So hi everyone, so I am Shuvomoy Gupta. I am a PhD student at MIT Operations Research Center, and I am going to talk about something somewhat non-trivial application of JUMP, which is constructing optimal optimization method itself using a methodology called BnB-PEP, and I implemented the methodology in JUMP. So before I start, I wanted to say something fun about me. So I was involved in one of the very first industrial implementations of JUMP. So if you go into JUMP and look into scheduling trains, so actually the paper that will show up, so it was done by me and my collaborators in 2016. So it was done in transportation industry, which is very safety critical and slow to move. And at that time, I needed convincing, like that, okay, we should use Julia and JUMP. So right now I am in the process of in another industry collaboration, like in the same industry. And this time, like I noticed that, okay, like I did not have to convince people as much in industry. So it I think, denotes that JUMP has made a significant progress like since then. So I felt that I should communicate this with you guys. Yeah. So, okay. So now I'm going to talk about what I was supposed to talk about, which is branch and bound performance estimation programming. So this is actually a way of generating optimal optimization methods. So I will skip a lot of the details. So if you are interested, so please check out the paper. It's accepted now and published in Math Programming. So what is the core idea? So the core idea is that, like we show in this paper, that if we are trying to find optimal first order method, basically gradient-based methods, we can find them by solving certain non-convex optimization problems. And we propose a custom branch and bound algorithms to solve these problems to global optimality. And using this methodology for several classes of setups, we found first order methods that outperforms the existing methods. And another non-trivial byproduct of our methodology is that it can systematically generate completely rigorous mathematical convergence proofs. Okay, so this is the outline. I will give very brief background how it works, some applications that we have found already, and concluding remarks. So background, the key problem in optimization actually is just this. So we are trying to minimize some function. This is our decision variable, and where f, the function itself, lies in some function class. And through indicator function, we can encode constraint optimization problem in this setup too. So in modern large-scale optimization and machine learning problem, the problem dimension n is very large. So to solve these problems, we usually use first-order methods. So these are methods that we can describe or analyze using gradient if it's differentiable, or subgradients if the function is not differentiable. So the classic example is subgradient descent, right? Like we have previous iterate minus some carefully chosen step size, subgradient selected at the previous iterate, and we combine them, we go to the next iterate. But it's only one algorithm. So there are like many, many more. And we can design our own methods, which was the purpose of BnB-PEP. So why first order methods? Because they are extremely scalable and they are very cheap computational complexity wise. And then they can be parallelized very easily. And most popular deep learning algorithms, they are first order methods. So finding optimal method to minimize the given function class can be of importance. So what is the definition of optimal first order method? So we show in the paper that this class is sufficiently large enough to optimize over this. So without going too much into the detail, if you look into the last line, roughly speaking, it means that the nth iterate is the previous iterate minus the span of the previous subgradients that the method has seen, and h and I is the learning rate or step size. So we denote the class of these methods through mn, and all the methods that I showed before, they actually fall in this class. So it's a sufficiently large class to search for optimal first order method. So what is going to change is the nature of the class itself. Like it could be an LP. What is the input that's going to change, like in this optimization problem? So what will change is the function class. It could be smooth, convex, non-smooth, non-convex, and so on. We show that it's actually a min-max problem where the outer mean is searching for the optimal method, and the inner mean, it kind of represents the convergence rate. So we are trying to find the method with the best convergence rate. So we can show that like going through a bunch of transformation, it can be formulated as a QCQP. I will skip all of the detail because I already see I have like 4 minutes left. But if you are interested, I have actually a YouTube talk where I go into the process of the transformation. So in the end, no matter what you do, based on the function class, it will be somewhat different, but structurally it will look like this. That there will be many constraints that are linear, but there will be some constraints that represent their non-convex quadratic constraints. And if you can solve them, we show that like the optimal step sizes that we find, they will be optimal, like exactly optimal in large scale setup, where the problem dimension n is much larger than the number of iterations you will give, which is the case in most large scale problems. So how it works and how jump is used in this phase is we do the implementation using Julia and jump, and the model itself, the modeling part relies heavily on the advanced features of jump. So what do we use? We primarily use the callback features heavily to modify existing spatial branch and bound solvers. So I will go into somewhat of the details in the rest of the 2 minutes. So these advanced features of jump, they were like extremely handy for me while I was coding up the methodology. So how do we solve this QCQP? So it's a 3-stage optimization problem algorithm. So first stage finds a feasible solution by solving a convex SDP. So basically it means that in this stage we are just trying to find an algorithm which will not blow up in terms of convergence rate. 3 minutes, okay, that's good. So stage 2, what does it do? It does warm starting. Again, like we use the warm starting feature. So this we solve using a interior point solver, and we find a local optimal solution. In the third stage, we warm start again with stage 2 solution and find a globally optimal solution. And this is where we use all the callback features to modify existing spatial branch and bound solvers. So how we do this? So in this phase, like jump was like extremely useful. We compute tighter valid bounds by solving an SDP regression. On the decision variables, we find improved lower bounds on the objective value. Again, this was done by solving through lazy callback constraint method. So then we, at each node of the branch and bound tree, we somehow modify the behavior of the algorithm by using custom heuristics. And also there is this thing called sparsity pattern of the inner dual variables. So here again, like we use like SDP relaxation. So I will give one example. So this is what would be the optimal method to reduce gradient of strongly convex smooth function class. So even though it's like seem like a very easy problem, so actually we did not know what is the best method to reduce gradient norm squared of strongly convex smooth function class. Okay, so I wanted to compare Gurobi versus our algorithm. So what I wanted to say that is much faster. And this is how you can see, if we compare our algorithm on the worst case performance measure, we actually find a near optimal solution like in 10 iterations in log scale. Okay, so last minute, so I will skip like all the things. One nice application that I wanted to end with is that if we have constrained convex optimization problem, and if we are looking for the optimal first order method, so the optimal method was not known, and we found the method recently in a new paper, which we call Optista. And what is interesting is that it also revealed a completely new structure in terms of the algorithm. Like if you look at the previous first order algorithm, they don't show similar structure. Yeah. So I am done. And I hope that like you will check out the paper, and I felt that I could not do this, like the implementation without jump. So, yeah.